This is work done with his co-authors Ji Song, Jaime Lien, Ivan Poupyrev, and Otmar Hilliges. This presentation is about interacting with Soli, exploring fine-grained dynamic gesture recognition in the radio frequency spectrum.
So hello everyone, thanks for introducing. Today I will present dynamic gesture recognition based on Project Soli, which is a joint work with Google ATAP. So, as we all know that the computing landscape is changing recently, we see growing popularity of wearable devices. For example, smartwatches and head-mounted displays. The line between the virtual and the real world is becoming blurred. The traditional keyboard or touch-based interaction paradigm is no longer suitable for these devices. So a new, natural, low-effort, and high-precision interaction paradigm is urgently needed. These are the type of interactions we want to enable. Importantly, we want to send small, precise gestures that don't involve large muscle groups. Our community has proposed various approaches to augment mobile interactions, often based on some form of camera. A camera-based method can provide high-resolution input. The gestures need to be always in the line of sight, and segmentation of the hand is always difficult. The size and energy consumption of the device can also be an issue. IR, proximity sensor, can alleviate some of these problems. However, the sensing fidelity is very coarse. Electromagnetic field sensing shares many properties we need to recognize in their gestures. However, it tracks many rigid body motion, and user instrumentation is needed in some cases. And the interaction is still coarse. Please note that this limitation is an inherent problem. The restricting factor is the long wavelengths used in prior work. A variety of Doppler effect-based input sensing method has been proposed. This can suffer from similar problems. In particular, the spatial resolution remains low. So, in comparison with those techniques evolved, we are looking for some different technology, such as Google's Project Soli. But the Soli is a solid-state radar sensor designed to be sensitive to small motion, robust to optical occlusion, and can work both indoor and outdoor, and potentially enable fine-grained nature a gesture interaction with low energy consumption. Soli is based on ultra-wideband radar sensing. It's developed with supporting micro-interactions in mind. The origin sensor looks like the big black box on the left. With 2 years of iteration, it's getting small. Right now, it can be embedded into a chip no more than the size of a coin and runs at 60 gigahertz. With very low energy consumption. Now, to give you an idea how small it is, please notice the pink box on the lower right corner. There is rooming, and the chip sits in the middle of the black protector. So, how Soli operates? Soli is based on ultra-wideband radio, which is an impulse-based system. It generates and transmits millimeter wavelength pulse to the transmit antenna at 60 gigahertz. The signal propagates in the environment. And once it meets the target, part of the electromagnetic energy is reflected from the target and propagates back to the receiving antenna. But the receiving raw signal is a superposition of all the reflected energy from multiple components of human hand. Well, next question, how to leverage the radar mechanism of robust gesture recognition? We see the raw signal from the reflected energy is difficult to interpret. The radar engineer provides several promising transformations in frequency domain. For more detail, you can refer to Jaime's SIGCHI paper. In our paper, we mainly leverage the range Doppler images for gesture recognition. It contains almost all information of the raw signal and encodes the motion sequence into a series of 2D arrays. To help you understand more about range Doppler image, let's show some example signal from the sensor. The video shows live range Doppler image generated from the sensor when performing several gestures. We are trying two static gestures with different poses. In the live range dot-plot images, we see that different poses get really similar scattering shapes, which shows our sensor has really low potential to capture spatial structures. However, it responds almost instantly to any dynamic gestures. We are doing finger sliding and wiggling gesture here, and we see the scattering patterns changes almost instantly to finger movement. We want to state that a Soli sensor operates on different principles than traditional radars. It cannot reconstruct spatial structure of a target. And we see that range double image is very abstract. It's still difficult to interpret. Unfortunately, we do know few facts about signals from this millimeter wavelength radar sensor. But please notice the signal patterns the video demonstrate. As our hand moves, we see the horizontal axis of the range double image corresponds to the velocity change of a tracked object, and the vertical axis corresponds to the range and distance variation of the target. So, to summarize, if you look at these individual frames, can you tell which gesture it is? It's difficult. But if you look at the whole sequence, then we can see that the dynamics carries information. And now we see this actually the fast swipe gesture. And we see the velocity, and we see these velocity dynamic patterns can explicitly tell us what gestures it is performed. So the take-home message is that the signal lacks information about spatial structures. We must find a good way to extract the features. But modeling dynamics will be the key in solving this problem, where we should find a model to fully capture the temporal inside the sequence. This makes application of traditional approaches to gesture recognition difficult. For example, hand-engineered domain-specific features from individual frames and try to classify on a per-frame basis perform very poorly on solid data. And a model incorporating temporal aspects, such as hidden Markov models, exist. But tuning this for gesture recognition is notoriously hard because gestures do not follow a grammar, such as natural language does. But here is what we want. A feature extractor is able to capture complex and hierarchical features, and plus a powerful models which can capture complex time series. So nowadays, neural networks are getting extremely popular in many domains. It's inspired by how human brain operates and use large-size data set to train a network with huge number of connections. It perform very well in vision and speech recognition tasks, which shares many characteristics with our signal. So, we start to solve our gesture recognition problem with neural networks. A convolutional neural network is a widely used feature extractor. In the convolution process, it uses multiple features to extract local patterns by sliding around the whole input. By stacking the convolution layers together, we implicitly learn different layer features. And recurrent neural network is designed specifically to capture dynamic information. It uses a memory cell, in our case, long short-term memory, to record temporal sequence visited. It passes through the whole input sequence, and the gate mechanism can track long-term information in a dynamic sequence. It has strong ability to implicitly model temporal patterns, and the whole model is differentiable and can be optimized in an efficient way. So we propose a combined model that stacks an RNN on top of a CNN. The CNN extracts features, and our RNN models gesture dynamics. I want to highlight that we train this model together. This improves accuracy by a large margin. So this means that during the training process, the input, or in our case, the range Doppler image, is fed into the model, and we will try to predict the gesture class. Where we see here the first 12 fails. But the error between the predicted output and the ground truth is back propagated through the whole network and over time steps to adjust all the internal parameters. After several iterations of training, the model learns to capture the dynamics in the data. But now we go back and give you an overlook of our system. We plot our pipeline into two steps. We record a comprehensive data set for training process. Well, we introduce a lightweight processing step, followed by a neural network classifier. The CNN learns the representations of each frame, and this learned sequence is sent to RNN. Well, by stacking the frames into sequence, we see the system recognize gestures. Please note that the softmax layer emits predictions for each single frame in the sequence. At the same time, the memory cell of RNN, in our case, our STM cell, passes dynamics encoding along the whole sequence. Okay, now let's look at some results. Here, we see several gestures from our gesture set. In the lower left, you see the probability evolution over time, again highlighting the importance of temporal information. There are some gestures, such as push and pull, we absolutely have to consider multiple frames to make good predictions. To evaluate our system, we connect an 11-gesture dataset. It's arranged into different subject and settings to fully test the performance of our system. We demonstrate the gestures by snapshots in this table. We arrange them into different categories, examine different properties of the sensor. The first 4 columns are micro-gestures, and the others are trajectory-based gestures. We build the gestures by iterations, advised by user feedback and the UI designers in Google. So, we start the experiment from a standalone CNN, where we see the CNN capture some patterns in a single frame. However, the accuracy is far from satisfying. We work one step forward by fitting the sequence of CNN extract features into RNN. And we see a large margin of performance increase, especially in the trajectory gestures, which make use of the memory ability of RNN. So we show our proposed end-to-end trend model. By connecting 2 models above and trend together, we see this model outperform all the previous methods, but reach the accuracy of 87%. We briefly show the gesture performance here. It's interesting to see that the correlation of different gesture groups. Please refer to the data analysis in the paper. As we are using RNN, we want to evaluate how well it captures dynamics. If the memory cell mechanism works well, the probability of giving a correct prediction should increase when we see more frames in a sequence. The plot on the left shows this statistic. The horizontal axis shows the time step of the sequence, and the vertical axis shows the evolution of probability giving a correct prediction. We see the softmax prediction on the right are mapped to the discrete prediction in the plot. As we can easily see from the trend of the lines, the system does provide confident prediction when it sees enough segment of the sequence. We highlight group of the gesture here, where we see these gestures can be predicted really fast, sooner than 0.2 seconds, almost instantly for user interaction, as the gestures encode strong characteristic in the signal. And let's see some other gestures. But this pair of gestures see difficulties at the beginning of the sequence. However, the model understands human intention after it sees enough segments in the gesture. This shows the power of RNN for dynamic modeling. We try another evaluation setting by average pulling the softmax of all frames over the sequence, thus emitting a single prediction for each gesture series. We see another 10% improvement. However, these settings introduce prediction delay and requires very accurate gesture segmentation. So, to conclude, we are working on a gesture sensing based on Google's Soli sensor, which aims to provide low effort and robust interaction paradigm with low energy consumption. We propose a neural network-based system, which is end-to-end trainable, and we conduct a series of experiments to prove our pipeline. We achieve 87% average accuracy on 11 gestures. As for future work, we will connect a larger data set, and we are working on algorithms to robustly spot segment gestures and also discriminate random motions. Currently, we see the sensor embedded in this watch can recognize simple gestures and can detect human hand distance. I'm now optimizing our system with Google to enable real-time processing and potentially porting the algorithm into mobile devices to enable rich gesture interactions. Thank you for your attention, and now I'm happy to take questions.
Okay. It looks like there's a question over there.
Hi. So I'm curious because over time you got a higher probability of that gesture. So I'm wondering, using our model, is there a way to model like which stage of the gesture you're doing? For example, I'm rubbing my hand to change the volume. Can I model whether it's 20% versus 60%? Is there a way to do that?
Yeah, thank you for the question. But this is a good point, because now we are doing the gesture recognition on the whole sequence. But we also can maybe just to divide the sequence into several micro gestures, which combine the whole, let's say, large sequence. Like for a swipe, maybe there's a fade in and a fade out. So maybe we can divide the whole sequence into multiple micro gestures. And we train this classifier on top of this micro segment, and perhaps it can solve your problem.
Ken Arnold, Harvard. Probably pretty related to that, but I was wondering if you'd thought about exploring continuous output spaces, like perhaps if you had bend sensors on your fingers or absolute position indicators to be able to predict that. And then from that information, it might be much more straightforward to train a large class of possible continuous gestures.
Yep, thanks. So you're meaning that we use more sensors to capture, sorry?
To instead of having a softmax over a fixed class of gestures, to instead try to continuously predict some ground truth measurement, like where your finger actually is, and then the designer can then define a gesture based on like a sequence of finger positions instead of having to retrain an entire network.
So it means like you want to further to use this statistic we connect to help to design gestures, right? Or sorry, yeah.
Oh.
I think you're talking about continuous post tracking. That's what a traditional radar approach would do, probably. And some folks over at Google are working on doing it with this sensor, but the sensing approach, the analog front end is different, and it doesn't directly allow for 3D tracking, rigid body tracking. So it's maybe possible, but not super straightforward.
Hi. Which challenges do you see arising when the sensor is going to become wearable and you have loads of movements in there, and people might go on a train or might do other activities which are not related to gestures?
Yes, I think it's a very good point, because we said this sensor is actually very sensitive to really tiny, small motions. So in a good way that these small motions actually help us to capture the really, really tiny and micro gestures. And the other way also bring a lot of variations and noises. And a way to solve our problem is that currently we are connect a really small gesture set. We invite colleagues in our institution to help to contribute. But we give some instructions of how to perform them in a rather restricted area. So now the network works with this rather clean data. So the good way to solve this problem is that we try to enlarge data set, because you see other tasks where you're using neural networks, like in image classification or videos, or you have a very huge database which contains really a lot of variations. Like we have cameras are really accurate and with high resolution, and we have ImageNet, which is pretty large, like millions or billions of pictures. So we can also build such gesture set, which is super huge. So it contains all the variations and even the tiniest motions that people will perform differently. It depends on the way you interact or positions, which neural network eventually learns these tiny variations and can do prediction really accurately after it sees enough data. Yeah.
Thank you.
One more question while the third speaker is
Hi. What was the field of view and the range of the gestures that you were evaluating?
You mean a field of view? Yeah.
And the range, so the distance from the sensor.
The current is quite small because we want to make it in like personal wearable devices. So like in a far distance, like 1 meter or 2 meters doesn't make sense. And also our antenna is pretty small, so the energy is pretty low to make it on wearable devices. So now it captures like gestures inside like 20 centimeters. And then in our case, so perhaps other application can enlarge its field sensing, but we are working on personalized, personal wearable devices, which now detect objects really close to the sensor.
Let's thank the speaker one more time.